Section 4.3. In the last section, I wanted to work through quite a few examples of computing Laplace transform so that we could start to build a familiarity with this operator. I don't expect that you'll be as comfortable with the Laplace transform as you are with, say, the derivative. If I give you sine of x and I ask you to enact the derivative, you can hopefully give me cos of x back without even really pausing to think. So, I don't think that you'll ever be that fluent with the Laplace transform, but I'm hoping that if you've worked through the lecture for 4.2, and if you complete the upcoming written homework and web work sets, you'll at least be able to take common functions and give me their Laplace transform pretty directly. Here's kind of an example. If I was to give you f of t equals 3 e to the negative 4t. I hope that over these next couple days you'll be familiar enough with the Laplace transform that you could just tell me that the transform would be 3 over s plus 4 without having to go to the integral definition and working through the full detail. And actually, like the derivative, we hopefully build up enough fluency that we can actually reverse the process. So say I give you capital F equals 3 over s to the fourth. Can you reverse engineer the lowercase f of t that came from? I've identified here that if I have a transform of 3 over s to the fourth, the original function, the lowercase f, would be 1/2 t cubed. Let me show you quickly how I would work through that. I recognize, as I've indicated here, that the general structure of my transform is a constant over s to a power. So that gets me thinking of the theorem from last time that the transform of t to the n, where n is a non-negative integer, will be n factorial over s to the n plus 1. And so this transform has the basic structure of this here. Specifically, it looks like I've got s to the fourth in the denominator. So what I do is I actually say, well, let me take the transform of, in order to get s to the fourth, I would need the power on t to be 3. And if the power on t is 3, then my numerator is 3 factorial. So in orange, I have some facts that I know to be true. Let me actually simplify this factorial over here. You'll see that this is 6 over s to the fourth. So now I take these facts, which I know to be true, and I compare them to the case that I'm looking at now. My f of s is 3 over s to the fourth. So I kind of compare a known transform, that is some transform that has like a known structure, to the transform that I'm dealing with. The only difference here is that mine is half as big as this known established transform. So I think I can accommodate for that difference by simply introducing a coefficient here as necessary. So just to verify, I said, well, let me try doing 1/2 t cubed to find the transform of that. That'd be 1/2 times the transform of t cubed. We've already identified that the transform of t cubed is 6 over s to the fourth. So that yields exactly the transform that I started the problem with. So that indicates that my little f must be this 1/2 t cubed, because if I take its transform, that leads me to the capital F that I started this problem or this example with. So in this example, I looked at the general structure of my given capital F. I tried to identify a known transform that has essentially the same structure, and then I just did whatever was necessary. In this case, it just involved introducing this 1/2 to be able to make those two line up. So if we start with a transform, a capital F, our goal sort of now becomes to imagine reversing the process to find the untransform or the inverse transform. We have a formula for enacting the Laplace transform, for going from little f to capital F. So is there a formula for going backwards, going from capital F back to the original little f? Yes, there is such a formula, but it's sort of beyond the scope of this class. If you'd like more details, let me know. But in the absence of a formula for directly calculating the inverse of a Laplace transform, what will our strategy be? Well, we'll actually just emulate the quote-unquote process I demonstrated earlier. Here, I've kind of laid it out in 4 steps. We start by analyzing the structure of the transform that we're presented with. We then, what I've called here coerced, we coerce the initial form of that transform into the form of some established family. Then we deal with the necessary details. This might be introducing a coefficient like we saw in the example above. Sometimes it's a little bit more complicated, but we basically just do whatever we need to make those 2 forms line up. And then we just utilize that structure of the established form to identify what our inverse must have been, what our original lowercase f of t must have been. For some cases, this quote-unquote process will be pretty straightforward, but then our goal in this section is to look at how we deal with less straightforward cases. I'd like to demonstrate some of the strategies we'll use by looking at some examples. In this example, we're presented with a few different examples of transforms, capital F's, and we're asked to identify the inverse transform, or the lowercase f function, that these transforms must have come from. In this first example, I have several fractions here. I know that I can take the transform of each individually, and my first step is to kind of just investigate the general structure of each of these fractions. These first 2 have the form s squared plus a constant in the denominator. The difference is that this first one has an s in the numerator, and this is just a constant. And this third one basically has the structure of a constant over s minus something. At this point, I go back to the notes from the last section, and I look for transforms which have those general structures. Over here in orange, I've rewritten a couple of the results that we got in the last section that I think will help here. Remember that the transform of sine of something is a constant over s squared plus a constant. That's more or less the structure of this second fraction here. This first fraction I now recognize as basically having the structure of the transform of cosine. And this third fraction, I guess I could factor 3 out of the denominator, and then it would be basically a constant over s minus a constant. So again, my first step is to sort of look over the results that I have to see if I can identify some transforms of known functions that have the same basic structure of the transforms that I'm given. Then I usually do 1 or 2 steps of algebra to make this capital F of s look more directly like the structures that I've identified. Let me show you what I mean. So here I just did some minor modifications to my capital F to make its structure more directly align with these structures here. For example, I have 3s in this numerator. I can clearly bring the 3 out front as a coefficient. And now this fraction, s over s squared plus 4, is exactly the transform of cosine of, I guess in this case, 2t. So I've just done a small modification, and I'll be able to very directly identify that this transform came from cosine of 2t. For my second fraction, I have s squared plus a constant, specifically s squared plus pi squared. So looking at the structure that's required for the transform of sine of something t, notice that the coefficient a is what is squared down here in the denominator, and it needs to be present in my numerator as well. So I clearly have s squared plus pi squared. So that means that this numerator has to be pi. Wow, but my original coefficient was just 2. So to accommodate the fact that I need that pi there, I've divided by this pi as well. So you can multiply this all out to verify that it will get me back to this transform that I had started the problem with. And then lastly, on this third fraction, I just factored a 3 out of the denominator and then pulled that fraction out front. This is clearly the transform of e to the 6t. So after one quick step of some simple algebraic modification, I think I'm ready to go ahead and identify what my original function was. As we've said, this term here will turn into cosine of 2t. The 3, that's the coefficient, just kind of is along for the ride. This next term I can untransform pretty directly as well. and similarly with this last term. So the inverse transform, or the lowercase f in this case, will be what's given here in my green box. That example was in fact pretty straightforward. I'm expecting that subsequent examples will get a little bit more complicated. Let's take a look at part B. In part B, I once again have a fraction for my capital F of s. And some of these terms look kind of familiar. I've got s squared. But I guess comparing to the forms that we saw in the last lecture, I am used to seeing a denominator that looks like s squared plus a constant squared. And I'm not used to seeing a denominator that's a full quadratic like this. So I don't think that any sort of simple modification will enable me to get this to look like the transform of sine or the transform of cosine. Actually, you know what? Looking at this denominator, it appears that it will factor. And then that kind of reminds me of the technique of partial fraction decomposition. Through partial fraction decomposition, I can rewrite this single fraction as two separate fractions that are split up over these linear factors that I just identified in my denominator. If you remember, the technique requires me to introduce unknown constants over those fractions, and then I'll have some algebra to do to solve for those constants. Before I do that algebra though, let me just see if this is going to help. Remember, I'm trying to untransform this function, and I definitely think that if I could rewrite it as two separate fractions with these denominators, then finding the inverse transform will be real straightforward. This looks like something times e to the negative t, and this looks like the transform of some coefficient times e to the 2t. So once I can identify those coefficients, I'll be able to find the inverse transform straight away. Here I have implemented partial fraction decomposition. There's a couple different ways to do this, and this is a technique that you utilized in order to evaluate integrals in a previous calculus course. So I would encourage you to review this technique if necessary, because I'll be honest, this is a trick that we're going to use pretty frequently in this section and the next couple sections. As I said, there's a couple different strategies or methodologies for implementing partial fraction decomposition. This may not be exactly what you're used to, but it's one of the valid techniques, and it has indicated that my A coefficient will be 2 and my B coefficient will be negative 2. And so my capital F is now in a form that I can recognize directly as being the transform of a couple exponentials. So from this form, I can state my little f, my original function, or the inverse, directly. So my little f is 2e to the negative t minus 2e to the 2t. And if I wanted to confirm that, I could easily take the transform of this function and hopefully get this as the Laplace transform. And then doing some algebra should return the original transform that I started with. So partial fraction decomposition is one algebraic trick that we can use to take a transform which does not initially have one of the forms that we're accustomed to and modify it so that it does have the structure of transforms that we can readily identify. Let's take a look at part C. In part C, my denominator is once again a quadratic, and just glancing at it, I can tell already that this will factor. So let me rewrite my denominator. So this transform can actually be written as 3 over s minus 2 squared. Once again, comparing this to the transform of cosine or the transform of sine or the transform of an exponential, this doesn't quite fit the structure of any of those. I've reminded myself off to the sides here that the transform of t is 1 over s squared. That's a result that we got in the last section. And this kind of feels like that structure. It's a constant over s squared. Well, it's not just s though. It's s minus 2. But if you remember from the last section, we have another theorem which yields not the transform of like a variable directly, but the transform of a shifted variable. Let me remind us of that theorem. This was one of our theorems from the last section, and it says that if we take the transform of e to the ct times a function, then the result will be the transform of that function, but not the transform just as a function of s, but as a function of s minus some constant. And that constant corresponds to the exponential that we've multiplied by. So that kind of feels like what's going on here, because instead of just 1 over s squared, I have 1 over s minus 2 quantity squared. So it's as if this s minus 2 is acting as my variable as opposed to just s. Let me rewrite this transform in a slightly different way just to make this structure a little bit more explicit. This is an exactly standard notation, but here I've just moved the 3 out front first of all, and then I'm saying I've got the expression 1 over s squared, but that's being evaluated at s minus 2. So that's telling me that I'm dealing with the transform 1 over s squared, but I'm evaluating it at s minus 2 as opposed to just s. So combining all these properties, I think my little f or lowercase f will be 3e to the 2t times t. Let me just kind of explain these ingredients. The 3 is obviously just along for the ride. The 1 over s squared is the capital F, which corresponds to t. So the 1 over s squared indicates that my inverse transform is t, but the fact that that function is evaluated at s minus 2 indicates, based on this theorem, that I have to multiply by e to the 2t in this case. So that will be my final answer. And this is another trick that we'll use pretty consistently. Specifically here, if I can rewrite my denominator so that it is a function of some s minus a constant, then I'll utilize this theorem to recognize that my function has been multiplied by an exponential. Let's keep rolling. Let's take a look at example D. For part D, I'm thinking partial fraction decomposition again. Here my denominator has already been factored for me. This s squared plus 2 term can't really be factored any further, at least in terms of real number factors. So hopefully you remember this little detail from when you were doing partial fraction decomposition. If I have an irreducible polynomial as one of the factors in my denominator, then when I go to break that fraction up, the numerator of the new sort of isolated fraction will be a general polynomial of degree 1 less. So in this case, I have s squared plus 2. So my numerator has to be a general linear polynomial. And then this linear factor, s minus 1, will yield one fraction as usual. Let me go ahead and work through the details of that partial fraction decomposition. So over here on the right in pink, I have worked through all of the steps to accomplish this partial fraction decomposition, and it appears that my original fraction can be broken down into these two fractions here. Now, partial fraction decomposition, I will admit, is pretty tedious and it can require a lot of steps, but let's look at the payoff. Now, if I want to find the untransform of this overall function, I'm presented with these two separate fractions that I can untransform pretty directly. And so going through all of this work here in order to be able to rewrite my capital F in this form seems like it's worth it to me. So what will the untransform or the inverse be? This is clearly a cosine term. Remember that when we're dealing with the transform of a cosine, this is the square of something. So I think that I'll have to take the square root of this, and then this is clearly an exponential term. So my little f will look like this, and as always, if I ever feel like checking, I can just put this f into the Laplace transform, use the established formulas that I have, and verify that the transform that I get will be this here. All right, let's keep going. Take a look at a couple more examples. Let's take a look at part E. Oh, I guess I lied. I guess this is our last part for this example. Once again, I've got a fraction that seems to be a recurring theme, and this denominator doesn't appear to factor. So in the previous examples, if you remember when doing partial fraction decomposition, factoring the denominator was pretty crucial. In this case, my denominator doesn't factor. And in fact, if I was to try to rewrite it maybe as a separate fraction, I've already got a linear numerator, so really there's no modification I can do to this fraction in terms of partial fraction decomposition. So I'm forced in this case to take a different perspective. Now, I recall from a previous example that there are some cases where instead of s acting as the primary variable, there's s minus some constant that acts as the primary variable. I'm not sure if this will work out in this case, but I believe that I could potentially get that type of algebraic structure in the denominator if I was to complete the square in the denominator. Completing the square is another algebraic technique that you've probably worked with in the past, but it may have been a while. So this might be something else that you want to review quickly just to freshen up on it a little bit. What I'm going to do here is I'm going to leave the numerator unchanged. And if you do remember completing the square, I sort of isolate the variable terms, and then inside this parenthesis, I'm going to add a new term. And that new term has to be selected so that what's in the parentheses is a perfect square. What I'm aiming for in my next step is something which factors perfectly as s something squared. So I have to introduce a new term in the parentheses here so that this will factor perfectly. And there's actually a little algorithm or a little formula for how I calculate that. I take this linear coefficient, divide it by 2, that'll give me -1, and then I square that. So I'm just going to add 1 here. Now, if I introduce a new 1 here, that changes the overall value of my denominator. So to make sure that my overall denominator doesn't change, I have to also subtract off whatever that new term was that I added. So completing the square really boils down to, in this case, adding and then subtracting a term so that this quadratic will factor perfectly. And if you look at it quickly, maybe you can identify that sure enough I'll have s minus 1 squared would yield this quadratic. And then I still have this term in my denominator, so I'll still have that plus 5. My numerator is unchanged. So now, thinking about structures of known Laplace transforms, this kind of feels like in the denominator like a cosine or sine term, because I've got something squared plus a constant. Well, but I don't have exactly s squared, I have s minus 1. So it feels like we're utilizing that theorem where I've taken cosine or I've taken sine and I've multiplied it by e to the 1t in this case. But before I can identify that solution, I have to rework my numerator a little bit. Let me show you what I need to do. If I'm going to adopt the perspective that s minus 1 is acting like the variable, then any variables, any s's that show up in my expression need to have that form. So what I've done here is I've forced my numerator to look like s minus 1. Well, it's not s minus 1. So what I did is I actually just did kind of the old trick where you add and subtract something, so basically it balances out to be what you need it to be. And again, this step is necessary because if I'm going to treat s minus 1 as the primary variable, then s minus 1 must be the variable everywhere it occurs in my expression. Now I can actually break this up into two separate fractions. And I recognize that this is a cosine term, or s minus 1 is acting as s. And then this is a sine term. I have to accommodate this coefficient. I'll have to divide by something, but this is essentially a constant over s squared plus something squared, where once again, s minus 1 is acting as that s. So let me write out what I think the inverse will be. So this is what I get as a lowercase f. So again, I'm recognizing that this is a cosine term, so that's why I've got cosine of root 5t. It has to be root 5 because this needs to be the square of the number. And then this, in this expression, I don't have s squared, I have s minus 1. Acting as the variable. So that indicates that I've multiplied in my time domain, in this function f, I've multiplied by the function e to the t. I have something very similar going on with this second fraction. I additionally have this coefficient that I need to introduce to account for the fact that my numerator ends up being just 2. Awesome. So we worked through quite a few examples. In these examples, we've demonstrated a few of the algebraic techniques that are going to be required to take an original transform, such as this one here, and manipulate it so that it becomes a form which we recognize as the transform of one of our common functions. Once we've done that work, then the process of untransforming is really just a matter of identifying the appropriate structure and then defining the corresponding functions in my little f. On the last page of notes, I have a few more comments about the examples that we've done so far, and then one more example that kind of ties all of this together. First, I just point out that it's not a coincidence that our Laplace transforms always seem to be fractions. That will, in fact, always be true. While there is one exception that we'll talk about in the next section, but otherwise, the structure of this operator is such that the output, the Laplace transform, is always a fraction. So when it comes to coercing our given transform into a recognizable form, this is always going to boil down to somehow rewriting our fraction. We've seen a few of the algebraic strategies that will be required in the previous examples, but I'll just point out that our author provides several examples of different cases, as well as kind of a refresher and some more details regarding some of these algebraic techniques. So I would definitely encourage you to look through this section in the textbook if you think you need a refresher on some of these techniques. In addition, so in the last section, we derived the formulas that we've used today. We don't really have the time or the energy to continue deriving formulas for all different types of functions. So usually at this point, we start to refer to some sort of table that displays the Laplace transform of lots of common functions. Our author provides such a table. He actually refers to it as a cheat sheet. Let me show you where you can find that on the website. Here on our textbook's website, if you click the home link, that brings up a page that has a bunch of resources. As I've mentioned, there are notes for several courses besides just differential equations. There's notes for an algebra course, for Calc 1, Calc 2, Calc 3. So if you ever do find that you want an additional resource to review any of these topics, these notes are available, and I think they're a pretty valuable resource. At the top of this page, he has what he labels cheat sheets and tables. And the last option there is a table of Laplace transforms. And if I download that table, we have a pretty extensive catalog of functions of t. Here he's labeled them as f of t or the inverse. And then the corresponding transform, which he's labeled as capital F or L of little f of t. Some of these are familiar. We have verified or developed rule number 1, rule number 2, rule number 3, etc. But this table goes into pretty significant detail identifying the Laplace transform of quite a few common functions. So as I mentioned in the notes, if you haven't yet, I would really strongly encourage you to download that table or a similar table and use that as a reference as you're working on Laplace transforms problems for this class. In the final example in this section, we're actually going to demonstrate use of Laplace transforms in solving a differential equation. In the previous section, we had an example where we applied the Laplace transform to an entire differential equation, but once we had done that, we stopped and we didn't push forward and actually try to solve the differential equation. Now that we have some practice with identifying the inverse transforms, we'll be able to push a step further and actually find the solution to the differential equation. So in example 2, I'm presented with this differential equation, y double prime plus 4y equals negative 16 cos of 2t, and I'm given initial conditions. What I would like to do is take the Laplace transform of the entire equation. I know that I can take the transform of the individual terms, and we have formulas or methods to evaluate the Laplace transform of each of these terms. Remember that for the unknown function over here on the left, I'll write the Laplace transform simply as capital Y because I can't provide any more detail than that. And we do have a formula that shows us how to take the transform of the second derivative of an unknown function. So I believe once I have implemented the Laplace transform on each of these terms, I get an expression like this. Notice on the left-hand side, I have a y of 0 and y prime of 0. Those are lowercase y's. So those refer to the value at t equals 0 of my unknown function and its derivative. But those are exactly the initial conditions that I'm provided in the statement of the problem. So I can plug in the values of 3 and negative 2 respectively in for these initial condition values. Next, I'll go ahead and move those terms over to the right so that the left-hand side just contains these capital Y terms. I'll go ahead and factor out the capital Y on the left as well. And now I can divide both sides by this quadratic coefficient on capital Y. Notice that this quadratic is exactly the characteristic polynomial of the homogeneous part of this differential equation. Let me go ahead and divide by that. Now that I've isolated capital Y in this equation, I'm actually in a position to untransform each of the terms on the right. And then when I untransform or find the inverse transform of capital Y, that will give me lowercase y. And in this context, lowercase y is exactly the solution to my differential equation. And so I'm now in a position to be able to just identify the inverse transform, and I will have the solution to this differential equation. So let's give it a shot. Again, I'll write the inverse transform of capital Y as lowercase y. These first two fractions are very familiar. Specifically here, this looks like this will be 3 cosine of 2t. This will be minus 2 sine of 2t. Now this third term is not exactly the structure of something that we are familiar with up to this point. I have s squared plus 4 in the denominator, which feels like a sine or cosine, but that denominator is actually being squared. So this cannot be directly untransformed to give me sine or cosine, and I don't think there's anything I can do in terms of partial fraction decomposition or any other algebraic restructuring of this, since it's basically as factored as it can possibly be at this point. So I think this is potentially a transform that we haven't encountered yet. So what I'm going to do is I'm going to take a look at the table provided in our textbook and see if I can find transform that has the structure of the one I'm looking at. Let me just remind myself what my transform is. This constant isn't really going to bother me. I basically have s over s squared plus a constant squared. So as I look at my table, again, the first few lines are some familiar ones. The next couple lines are actually quite different. Here's sine, which we recognize. And then here, entry number 9, I have s over s squared plus a constant squared. There is, of course, some coefficient, and I'll be able to accommodate that. I'm not too worried about that. But it looks like this is the structure of the transform that I'm looking at right now. Let me actually copy and paste that for reference. Here's that line from the table for reference. And sure enough, I've got s over s squared plus a constant squared, that entire quantity squared, and that matches the structure of the transform that I'm looking at. So I believe my inverse transform will be t sine of, looks like my a in this case will be 2, and then I just have to accommodate this coefficient. Let's see, if I took the transform of t sine of 2t, then my numerator would be 4s. The numerator that I actually have is 16s, so that means I must need to multiply by an additional 4. So there is the final solution in terms of the untransform. And then in the context of this problem, that is the solution to this differential equation. I guess we actually have an initial value problem since I was given initial conditions as well. So the methodology for using Laplace transforms to solve a differential equation involves taking the Laplace transform of the entire equation, incorporating initial conditions in as necessary, and then algebraically isolating capital Y, And then once we've done that, we can look at the terms on the other side and do what we need to untransform those terms. And then that overall function will be the solution to my differential equation. Now you might look at this differential equation and say, well, that looks awfully familiar. That's exactly the type of differential equation we could have solved in chapter 3 using either undetermined coefficients or variation of parameters. And that is true, but there are potentially some advantages to using Laplace transforms. First of all, notice that I didn't get a general solution and then after the fact have to incorporate initial conditions. I incorporated those initial conditions early in the problem, so I didn't have that additional step that we often do using other techniques. Also, if you look carefully at the structure of this particular differential equation, my characteristic polynomial, we identified that down here, would have roots plus or minus 2i. Therefore, my homogeneous solution would be a constant times cos of 2t and a constant times sine of 2t. In fact, I see those terms exactly in my final solution here. But then comparing with that in mind, if I look at this non-homogeneous term, this matches one of the terms in my homogeneous solution. And so if I was using undetermined coefficients, I'd have to go through the additional step of accommodating that repetition. All of that is taken care of automatically through this methodology. I don't have to modify my technique in any way. I just followed the same process, and all of those mathematical details are taken care of. So those are some potential advantages to using this technique as opposed to the techniques we saw in chapter 3. And as I note at the bottom of the page, there are actually some functions that we'll encounter in the next section which are pretty difficult to incorporate into an initial condition context. Specifically, there's discontinuous functions that we will want to use as our g of t. And using chapter 3 techniques can be kind of tedious and pretty difficult. And as we'll see, dealing with those types of functions while using Laplace transforms will be pretty efficient. So that's what we'll take a look at in the next section.